Okay, guys, it looks like you just got done with writing down the first part of section 4.4, some of the math speak, and one example of that, of evaluating integrals as well. We're going to do 3 more examples. I've got 2 of them up here if you want to start writing those down. We're going to do 3 more examples. I'll do these 2, then erase, and then we'll give you time to pause the video and to work on a portion of your assignment. And then I've got one other example we'll take a look at after that. Okay, so for example, the next example, we're going to evaluate the integral from 1 to 4 of 3 squared x dx. First thing we may want to do here is rewrite this as x to the 1/2 power. Okay, at the same time, I'm going to factor the 3 out in front. So I'm going to do 2 steps in 1. So I have 3 times the integral from 1 to 4 of x to the 1/2 dx. Again, if you needed to pause the video or need to rewind quick so that everyone in the class has these examples written down, you can. If we integrate here, this would give us x to the 3/2 times 2/3, and then we also have to multiply times 3 out in front. And we're going to evaluate that from 1 to 4. Okay, again, the 2/3 comes from, if you divide by 3/2, it flips and becomes 2/3. All right? Notice you can simplify this just a little bit, and you can cancel out your 3's. Okay, so now I've got 2x to the 3/2 from 1 to 4. Next step, substitute your upper limit in for x, and then substitute your lower limit in after that, and subtract those results. So I'd have 2 times 4 to the 3/2 minus 2 times 1 to the 3/2. And if I calculate that, 2 times 4 to the 3/2, oops, I'm on the wrong page here. 2 times 4 to the 3/2 would give us 16. And again, you can just use your calculator for that. And then 2 times 1 to the 3/2 would just give us 2. So if we evaluate this original integral, we get 14. So that's the first example. If you need to pause for a moment and get caught up and write that down, you can. I'm going to start, or I'll go ahead and go on to the next example. Our second example has the integral from 0 to pi over 4 of secant squared x dx. Again, the first step here actually would not be to factor or anything like that. We can just integrate this. You may want to use page 250 in your book to help you out with that. If we integrate this, we would have tangent x, and we'd evaluate that from 0 to pi over 4. So we've got that set up to be evaluated. Next, again, just like before, substitute your upper limit in for x and subtract that from the substitution of your lower limit in for x. So again, I'll write that out. We'd have tangent pi over 4 minus tangent 0. You can use your unit circle or you can use your calculator to figure this out. But tangent of pi over 4 is going to be 1. And tangent of 0 is just going to be 0. So this would evaluate to positive 1. Again, you can pause for a moment, the video, if you need to get that written down before we do our next example. I'm going to erase this now. Again, remember, you guys, I'll share this with you on Google Docs. And by the time you see it, I will have shared it with you on Google Docs, so you can rewind it at home and watch it again to slow things down or check over anything you might need to. One more example of evaluating, and then we'll allow you guys some time to practice this on your homework. We'll do an absolute value function. These are a little trickier. We're going to evaluate from 0 to 2 the absolute value of 2x minus 1 dx. We're going to use one of the properties we learned yesterday where we can split this into 2 different integrals. We're actually going to change our upper limit when we do so. In order to determine what we're going to change the upper limit to, we have to set the function inside the absolute value equal to 0 and solve for x. So I'm going to do that off to the side here. We have 2x minus 1 equals 0. Just add the 1 and divide by 2. We got 2x equals 1. Again, divide by 2. We get x equals 1/2. So instead of having this from 0 to 2, we're going to split that at 1/2. We'll show you what that looks like as we go back over to the integral here. So as I start to integrate this, I would have the integral from 0 to 1/2 of 2x minus 1. And there's one detail you have to remember about the first part of these absolute value functions. It switches to a negative. I'm not going to explain it right now on the video, but you can just trust me with that part right now. We'll add to that then the integral. Notice our lower limit changes to that split value of 1/2 to 2. And then the absolute value part stays positive, 2x minus 1. Notice, even though we split this into two pieces, we're still covering the original interval from 0 to 2. Again, the first part switches to a negative. This becomes positive. It stays as 2x minus 1. Now we can just treat this as two separate integrals that we know how to do. We can integrate this by integrating. You could first distribute if you want to. I'm just going to rewrite that in here. Just real briefly, we can make this negative 2x plus 1. So we're basically integrating negative 2x plus 1. If I do that, I would have negative x to the second plus x. And I'll evaluate that part from 0 to 1/2. Plus, if I integrate here, I would have x squared minus x. And I'll evaluate that from 1/2 to 2. Now it's just a matter of finishing our calculation. Substitute the upper limit in and subtract that from the lower limit. I'm going to set up some brackets to keep this part separate from this part. In fact, I'll write those in here right now. So we want to keep this part as its own calculation, and then we'll add it to what the result of this evaluating gives us. So if I put 1/2 in for x squared, so I've got negative outside the parentheses, 1/2 squared plus 1/2. The nice thing is that's just going to be, if I put parentheses around that, that's just going to be minus 0. So I'll put 0 in for the x's, so I just have minus 0. If we work on this part over here, okay, we can put 2 in for x, so I'd have 2 squared minus 2. Now minus the lower limit, put 1/2 in for x, 1/2 squared minus 1/2. From there you can do just some calculated work and that type of stuff to get this problem finished up here. So let me fix this. Minus sign there. Excuse me. If I have 1/2 squared, that'd be 1/4. So I have negative 1/4. I'll write a note here. Negative 1/4 plus 1/2 minus 0. That's going to result in positive 1/4. So this first part here that we split from 0 to 1/2 evaluates to positive 1/4. Now we need to make our calculation over here. 2 squared would be 4 minus 2, which is 2. 1/2 squared, again, is 1/4. 1/4 minus 1/2 would be negative 1/4. And then finally, 2 plus a fourth would be, 2 minus a negative 1/4 would be the same as adding, so we'd have 2 and 1/4. And so we can finally then combine those two parts. 1/4 plus 2 1/4 would equal 2 1/2. You can write 2.5. You could write it as 5/2, however you'd like to write that solution. Okay, so you do have two problems, 23 and 25, that are like this using absolute value. For the next part, I've got one last example. What I'd like you to do right now is take a moment actually take, we'll say 15 to 20 minutes here and start on your assignment. This is enough information to do numbers 5 through 33 and possibly even 35 and 37. So take about 15 to 20 minutes here to work and pause the video right now. And then when you're ready, after that time, we'll do the last example together. Okay, let's do that last example. For those of you who have motion sickness, you may want to avert your eyes for a moment. I'm going to move over the computer over to the other board so you can see this last example. I've got it prepared already. So you may want to look away for a minute. I'm going to move the computer so you can get this last example. Okay. So that's set up here. The instructions for this tell you to find the area of the region bounded by 4 functions. Y equals 2x squared minus 3x plus 2, x equals 0, x equals 2, and y equals 0. A couple things to note here. These would be vertical lines. All right? You could actually do this without drawing a picture, but I'm going to draw a picture because there's a couple on your homework where the picture is already drawn for you. So I want you to kind of see what that looks like. You guys know that we could figure out what this looks like rather than using an XY table by putting that in our graphing calculator. So I'm going to draw the graph over here. I'm just going to draw a quadrant 1 graph because that's where we're working for this example. So we have 0, 1, and 2. And again, this is just kind of a sketch of what this might, about what this would look like. Okay, but that black curve here would be this curve y equals 2x squared minus 3x plus 2. Okay, I'm going to draw these in purple. Hopefully you can tell the difference. These would be vertical lines. At x equals 0, right on the y-axis, and at x equals 2. And then finally, y equals 0 would just be the x-axis. So you can see we're finding the area inside here between the purple lines. Okay, that's the area we're calculating, and we could shade that in. Part of what you'll have to do then is use this picture, and there are other problems like this, 35 and 37. You can use this picture to set up an integral. Notice, as we set this up for our integral, we want to focus on the x values for our lower and upper limit. Notice our lower limit would be 0 to 2. We could have done that part without the picture by noticing that we have x equals 0 to x equals 2. So there are multiple ways you can do this. The function that we're integrating is y equals 2x squared minus 3x plus 2. You can see how this would eventually lead to being able to calculate the exact area of what's underneath this curve, that shaded region. So you can start to see how this is useful with these integrals to find areas of curved or just oddly shaped regions. Now that we have our integral set up, we can calculate this out, or excuse me, we can integrate this, substitute our upper and lower limit in, and calculate the area of this region. One thing I forgot to add was this area would equal this integral, and we're doing this with respect to x. We're using dx. As I integrate this, I would have x to the third, and so my coefficient becomes 2/3 when I divide by 3. Notice here I'd have x to the second. My coefficient would become 3/2 when I divide by 2 plus 2x. I'm going to evaluate that from 0 to 2. Again, like we've been doing, substitute in your upper limit and then your lower limit. I'm going to do this over here so it doesn't get too low on the board. I'm going to use parentheses to do this as well. We'd have 2 times 2 cubed over 3 My screen just went black. That was weird. Okay, I'm still recording though. Move it over. Sorry, strange pause here. First time doing it. 2 times 2 cubed over 3 minus 3 times 2 squared over 2 plus 2 times 2. And then the nice thing about this one is we'll subtract this. We're putting 0 in for x, so my second parentheses is just going to be 0. Works out a little nicer than we might have at first expected. So now let's just evaluate this and simplify this so we get a solution for the area. This would be 2 cubed would be 8 times 2 is 16. So we have 16 over 3. 2 squared is 4. 4 times 3 is 12. 12 divided by 2 would be 6. And then 2 times 2, we have 4. So we have 16 thirds minus 6 plus 4. And you can put that all in your calculator at once, or you can choose to work out a common denominator, however you prefer. But what we find out is that our area is 3 1/3 units squared. You could also write that as 10 over 3 if you like, whatever you would prefer for that situation. When I come back tomorrow, I'll be able to answer a few questions, but I think you'll have a pretty good handle on this fundamental theorem of calculus. This will allow you to do numbers 5 through 43 odd, which is about the first third or close to first half of your assignment. We'll work on this some more tomorrow and add on to section 4.4, and we'll do that some more on Thursday as well. Look forward to seeing you tomorrow. Again, I'll share this with you on Google Docs, and that way you can go back and view it at home as well in case you need to slow it down or just want to go back and see how to do any of these examples.